Well, welcome everyone to a delayed start for this IARPIC meeting. I'm Joe McGregor, glaciologist at NASA Goddard Space Flight Center. I'm co-lead of the Glaciers and Sea Level Change team with Caitlin Harbeck and Zoe Corville, who are also here. And today we want to hear about glaciers through time from air and space. And the motivation for us for this meeting was there's been a lot of work recently. Oh, someone say something? Sorry. There's been a lot of recent work looking at satellite imagery, looking at historical aircraft photography, studying glacier change over time to better understand what we might be expecting in the future. So we thought we'd hear from some folks who've been studying that problem. So today we've got Christopher Shuman from UMBC and NASA Goddard, who'll be talking about northeastern Greenland, and also Jack Kohler from the Norwegian Polar Institute, who will be talking to us about a recent study of Svalbard glaciers over time. So that's both exciting areas for us. We don't hear about Northeast Greenland or Svalbard terribly often in this meeting. Or in this group, so these are nice to get a little more geographically farther afield. And yeah, due to the delay, we'll just go ahead and get started. We're going to hear two roughly 15-minute presentations from Christopher and Jack, and then we'll sort of open it up for comments. So again, thanks for bearing with us. Sorry for the delayed start. And Christopher, do you want to go ahead and start?
I'll give it a go. Let's get that in full screen.
All right, okay. That's working.
Hey, let's hear it for tech, when it works anyway. So this is a collaboration with Mark Fahnestock that began as part of a proposal and ended up drifting into a presentation form rather than a proposal form. And so it's Northeast Greenland and the power of playing in the Landsat archive is more or less how we got here and what we can learn from that archive. So without further ado, I think everybody knows the area generally, but if you don't know, Zachariæ is essentially the biggest outlet from the Northeast Greenland ice stream, or some call it the Zachariæ Isstrøm. So this is based on the AGU presentation that Mark and I put together last December. And I'm sure nobody saw it because there were tech issues there too. All right, but first a little nod to Landsat. It basically is one diagram that's trying to summarize just an incredible record of Earth imagery, the longest continuous publicly accessible record. And it really is a tribute not just to the engineering, but all the people that made the Landsat program happen over the years. So this is really my pleasure to explore these data and to share them with you today. And this, of course, has been made possible in part because the Landsat data became free back in the 2000s. And otherwise, I would not have been able to download all the imagery that I needed to get this presentation together. Really some visionary people back in the fairly early portion of the space race decided that not just looking outward, but looking backward at Earth was going to be very important to do. And the initial proposal didn't include NASA, oddly enough, but very soon came to be a joint program between the United States Geological Survey and NASA. And the people that are now long gone. Really, they deserve our thanks for seeing what could be. And I'll try to make that case here. I really have to give a nod to Laura Rocchio and Ginger Butcher and the folks on the Landsat project office that put together the longer version of this talk. And there's just some gems in here. The fact that we took the first model of what would be Landsat 1 and brought it over to Goddard and promptly broke it in the centrifuge. So the original name was a real mouthful, Earth Resources Technology Satellite, and thankfully they renamed it shortly before the launch of Landsat 2 in early 1975. There's a fun little documentary available from the National Archives. If anybody wants to see that, I'll send that around or put it in the chat later. And Landsat 1 launched in July of 1972. And that has just set the foundation for the continued acquisition of Earth imagery, especially of the polar regions, because of the convergence of orbits. But one of the little backstories that most people don't really know too well is that the primary instrument was going to be a TV camera-like sensor, similar to some that had flown on early weather satellites, and an experimental sensor, the MSS, the multispectral scanner, was developed and put on board and has become the foundation of all subsequent digital scanning sensors on orbit, although of course technology has developed in many different ways. But Virginia Norwood really deserves our thanks, and she was a real treat to visit with when I was at the Landsat 9 launch. Lots of stories, but you know, hard to imagine, you know, what it took to get that first sensor up on the platform and launched. Nowadays, we kind of take the availability of Earth imagery for granted. There's any number of different satellites on orbit, helping us to understand what's going on around the globe. Although Landsat 9 rapidly disappeared into the marine boundary layer in September, the sonic booms are just unforgettable. If you've never gotten a chance to go to launch, it's really tremendous. So here we are now, you know, with Landsat 9 and 8 both on orbit. Turns out Landsat 7 in a lower orbit is still acquiring some images, but its orbital crossing times are changing. So they're kind of doing it as a test of what can be gleaned with the sensor on Landsat 7. But Landsat 8 and Landsat 9 are performing spectacularly based on the science team meeting out at Sioux Falls last week. So without further ado, this is what I was able to glean from the archive, and I'm not trying for annual resolution for the very good reason that that wouldn't be possible, especially in the early portion. And you'll see, let's see if I can use my cursor here. You'll see how I've pasted together images from different dates, and when they're just a very small portion of the image, I don't give the date for them, but these are all, of course, in the imagery stack over on the image processing computer. But there we are in 1975, first well located and clear MSS image that I could find from Landsat 2 in August of 75. And so you can see, you can get hints of the motion and even the loss of some birds by September of 1980. Down here, there's a little bit of loss, and there's a little bit of motion within the basically, hard to describe it fully as an ice shelf, but I'm calling the entire floating ice area out front of Zachariæ an ice shelf, some of it more solid than the other areas, but it's moving, and it's evolving, but still healthy in 1980. By 1985, you can see those birds are beginning to move a little further south. So The fastest flow is down along the coastline here, where there are no tributary glaciers contributing ice into what will be open waters, as I suspect everybody on this call knows. By 1990, there's some further losses on that western side, but the rest of the front hasn't really changed much. So there's this developing stress field, which is suggested by the sequence of images. Mark has a movie version of this, but I'm not going to play that here, in part because of, well, chances of tech issues. So by 1995, there's been a whole lot of change over on that western side. In fact, that open water is suggestive of what has caused some of those ice losses over on the western side, and the mottled character of the Greenland sea ice cover suggests this was a pretty warm period in 1995 and again in 1999. And there's a good deal of surface melt as well, right at the beginning of the Landsat 7 era. And basically, you can read the writing on the wall, if you will. And then, well, the acquisition plan was not favorable, shall we say. And so I had to piece together the images in 2000 and 2001, because for reasons which are not entirely clear, they just weren't acquiring a lot of images in those years. And it gets sadly even worse in 2002. There is a complete view of the developing melt season in June 2002. And then there's only partial coverage of what is the breakout event, where right south of Schnauder Island, the icebergs finally popped loose. They also popped loose on the west side during what was a very low sea ice period, as you can sense in the partial Landsat coverage over here in September of 2002. I paired it with a MODIS natural color image, so you can get a full sense of how rapidly the shelf area broke back inland. You can actually see this pretty clearly in MODIS. Early August was the crucial time. And that break of the floating ice continued into the scanline corrector off era with Landsat 7. That's what those lines are. It's my best attempt to make a full composite of the same area with Landsat 7. They fortunately turned Landsat 5 back on in this area for some years. There's good coverage, and so you can see that break back into what is the ice stream proper, the glacial outlet, continues between 2003, 2006, with many new bergs coming free from both the glacier front as well as the abandoned portion of the ice shelf that's gradually being disconnected. And some of the old bergs are still floating around down here, adjacent to the fringing islands, and we'll see them a little bit as we go forward here. By 2009, you can see that the remnant, the shelf remnant, is really very well detached, and there's ways of getting a close-up view of when it stopped receiving ice from the Zachariæ Isstrøm's outflow. And then that's the last Landsat 5. Unfortunately, we shift back to a Landsat 7 scanline corrector off in 2012. And then the disconnect is really obvious in the first Landsat 8 that I pulled into the series. The shattered bergs are very numerous across Jökulbygden, and if somebody knows how to properly pronounce that, I'd be grateful. And then by 2018, the losses from the Zachariæ Isstrøm front continue, and the sea ice ebbs and flows in the bay, and that has some impact on the rate of calving from the Zachariæ front, and sort of as an interesting aspect of all this as well. By 2021, the low sea ice is pretty obvious in this early August image, and some of those old bergs are still drifting around, caught in what is apparently a bit of a gyre where there's warm water flowing up, which may have contributed to that loss of ice cover earlier in the time series. You can actually see some of the bergs drifting around up here by the Zachariæ in a circular fashion. So the icebergs make pretty good drift markers. Just to give you a sense of the magnitude of the area loss, the total outline in blue there, it's a bit of a sketch to determine what you consider an ice shelf, but at any rate, about 3,100 square kilometers of ice area lost in Jökulbygden since the early years. And that just gives you an idea of the magnitude, which perhaps is a little more obvious when you compare the 75 and 2002 to 2021 images here. And that's just I think maybe not as well known as it could be. And so Mark and I are working on that basis, that we've learned something looking at the Landsat archive, and the magnitude is pretty dramatic for what was Greenland's largest ice shelf. And I promised Joe that I would put a 2022 image. And so what I can show you down there at the bottom, underneath a couple of the bullets, is the basis of a hyperwall, which is in development for release, hopefully before AGU, that shows you just how far back inland the Zachariæ ice front now is compared to just prior to the breakout southeast of Schnauder Island. So there you have it. I could read the bullets, but I think they're more or less summarized in what you just saw. And so I'll end with a little nod to that ice area loss being roughly the urban area of Miami. And we pick on Miami because, well, let's put it simply, it's really close to sea level. So this is going to have an impact as it continues to push mass out into the global ocean. And one small nod to the folks who worked at the USGS to generate these early illustrations of change for glaciated areas around the globe. This old oblique aerial photograph and others are getting scanned in by some collaborators at Ted Scambos, and so we'll hear more about those in the future, and maybe from Jack quite shortly. Thank you for your time.
Awesome. Thank you, Christopher. Really, wow, great overview of what's been going on there. Any quick questions for Christopher? We'll probably try to combine questions until the end, but any quick ones for Christopher while we're here? Jack did.
Yeah, I was just right on your second to last slide, Christopher. You mentioned some work at how much thinning and whether the ice stream is accelerating. Is that work that you're involved in, or others working on that? I'm just curious how much drawdown you've seen.
Mark and I are working on that currently, but I know there's a paper coming out because the grapevine is very effective at transmitting work in process. So I know there will be news on exactly how much drawdown there has been, and also how much faster the ice is now flowing now that there's essentially nothing in its way. So stay tuned. I am only peripherally involved in that paper, however.
Thanks, Christopher. Could you share your second to last slide again real quick? There's a feature I want to try to make sure I understand. Yeah, this slide before that. So on the 2022 image, there's
Okay,
one.
there we go.
Yeah, I get. Yes, thank you. So you've got Zachariæ on the left. In the middle, you've got you've got. Is that the brightness of the melange in the center of the image versus what's farther to the southeast? What are the differences between these areas? Is that central area the sort of the dynamic part of the melange that's influenced by calving events, and then the other part is more static, or is that just sea ice? What's your understanding there?
What's under the label Jökulbukten is a fairly coherent sea ice cover.
Okay.
And so that is not there in the 2021 image. And so all the calving is pushing out against I'll call it first year ice because I'm sure it's not there in 2021. And we can go back one slide if you want to see that. But the very modeled patterns on the outflowing glacial ice are a bit of a mystery to me, because it could be differences in dust accumulation, in melt intensity, a number of different things which are happening in this RGB image pair.
Yeah.
And if you look at these long enough, you begin to just appreciate them for the story that you can't quite figure out, that there is a lot of dynamic surface activity going on, as well as the interaction between the glacier front and what's passing from melange now in the bay. So we'll get the movie together from Mark and take a look at it, because that'll tell you a little bit more. Okay.
Great. Well, thanks so much. All right, Jack Kohler, ready to hear from you.
Okie dokie. I wasn't quite sure who the audience was for this, so I might delve a little bit into stuff people already know, but about mass balance. You're hearing me, I presume. No one's stopping me. Yep, good. All right. So mass balance. What is glacier mass balance? Well, it's simply a bit of accounting, looking at what falls in the winter as snow and comparing that with what melts away during the summer. And then the balance between these two is the annual glacier mass balance. And why are we interested in that? Well, if there's more melt than there is accumulation, then water flows down the glacier and out to sea and contributes to sea level rise. And that's the motivation for what we're doing here, looking at mass balance. Now, potential total sea level change, everyone knows that if Greenland melts completely, then sea level rises 7 meters. If all of Antarctica melts, it's almost 60 meters. And all these little small glaciers in blue around the world only contribute to sea level rise with about 30 centimeters. So not so much, right? But one of the last sea level budgets, the last one that I have available to me at the moment, current sea level rise is a little over 3 millimeters a year. And it's partitioned between 1/3 to expansion of the water due to upwarming, then 1/3 to Greenland, Antarctica, and to terrestrial water storage. And then 1/3 are these small glaciers. So the small glaciers in the long run don't mean too much of sea level rise, but for the moment, they are very important, extremely important. And so it's contingent upon us who work on these small glaciers to come up with estimates to help close that part of the sea level budget. And my little piece of that puzzle is up here in Svalbard in the far north, east of Greenland. It's about 60,000 square kilometers and 60% covered with glaciers. And there are over 1,000 glaciers that are larger than 1 square kilometer. The mass balance program that I run in the area of the science town of Ny-Ålesund, it's comprises 4 glaciers ranging in size from 5 square kilometers to over 400 square kilometers. And I'd love to tell you all about how we measure mass balance in the field, but time is limited. So we'll just present the basic result that we get from looking at each individual glacier. We have 2 visits, one in spring where we estimate the total winter accumulation since the previous fall. And then in fall, we go back and see how much snow and ice has melted. And then you add those 2 terms together and you get the net balance. And in the case of this small glacier, Isstrøm, which is the longest time series going back to the mid-60s, you can see that the net mass balance is very consistently negative, only 3 years where it's positive. And it's losing currently something like, on the average for this period, 60 centimeters of water equivalent per year, disappearing, averaged over the entire glacier surface. So that's great. They're the 4 glaciers that I monitor in Jolesund, and then another one that NPI is responsible for in Nordaustland. And then other institutions measure mass balance at a handful of glaciers around the archipelago. But what about the rest of Svalbard? How are we going to estimate the total mass balance for all of Svalbard? We can't measure mass balance on all the glaciers. Obviously, that's logistically challenging. So we either turn to models, or we can use remote sensing. And that gets us into the next way to look at it, which is to do the geodetic mass balance. And this is based on making observations of the glacier surface at one time. So we have the glacier elevation at time 0. And some later time, we come back and find a new elevation. And then the difference at any arbitrary point is simply dz dt, the difference in elevation there divided by the time interval. And if you were to integrate that over the entire surface, here the integration is lengthwise, but in 3 dimensions, it's over the area. The integration of that volume is exactly equivalent to the integration of the mass balance you would measure in the field over time, with a small correction factor for the difference in the densities of ice versus the meters of water equivalent. So you just sum up the mass balance measurements, the black bars there, and that would be equivalent to the difference you would get if you had 2 maps, one from 1966 and one from the present. So that's very trivial. If for one glacier, you can usually find 2 or 3 or more maps where you could do such a difference exercise. Problem is, for all of the archipelago, there has not ever been a complete DM covering the whole area. So for the first period pre-1990, we have reasonable spatial coverage except for the far northeast, but it's spread over many years from 1936 until the 80s. In 1990, there was a big aerial photography campaign, but making maps from that was never completed. And so there are big holes in that coverage, which is good temporally, but poor spatially. Finally, in the 2000s, we start to get good spatial coverage. It's over the whole decade, but these are satellite products. And they are spread over the decade, and they are not as high quality as the aerial photography derived products. But now, finally, we have a DM covering all of Svalbard, which is more or less one period. And it's based on aerial photographs that were collected by the Polar Institute between 2008 and 12, mostly in these 3 years. So I call this the 2010-ish DEM. And that is now the basic product, and allows us to do all sorts of interesting comparisons. As part of that DM, we can also then generate an orthophoto, and that will come in handy, as we'll see. So that's our reference DM. Now, what about the previous data? Well, let's go back to 1936, when this man, Bernard Lunke, who worked at the predecessor of the Norwegian Polar Institute, who was a pioneer in aerial photogrammetry. He traveled up to Svalbard with this small plane and a crew. And photogrammetric quality camera in the tail of the plane, and they flew around and took a series of oblique aerial photographs. And of course, the principle here is that by looking at the same thing from two different angles, you can generate contours, as I will show. And they collected in 2 years, 36 and 38, over 5,500 photographs covering nearly the entire archipelago, missing only a little bit of Nordaustland. And then the idea is you would take each image pair and put them in this very complex apparatus, and by looking at them and bringing them into focus, mechanical linkages will allow you to generate contour lines and thus make maps. And this allows you then to go from these rather schematic maps, which were produced in the early 1900s by the first explorers of the area, and then start to make very accurate maps with contours you could actually use in a quantitative sense. And this sort of approach was what we used in the 1900s. Nowadays, we use a computer, and we don't generate contour lines, but we generate digital elevation models, grids of elevation data. But the principle is still that we would work pairwise with images, generally speaking, until recently, when we start to see the development of structure for motion software. And the idea here is that if you have many, many pictures of an object taken from all sorts of different angles, you can throw it into this kind of software and generate a 3D point cloud of that object. And you can see this in this basic 3-picture GIF of a fire hydrant. And just by having a few images taken from different positions, you can start to get an idea of the spatial orientation of them. And then in the software, you can generate point clouds. You still don't know exactly where they are, but if you were to be able to put measurements to them, then you could generate an accurate model of the object. And that is the basic tool that then was used in the generation of this paper, which came out in January, and it has a bunch of other co-authors, but the star is Emily Gaiman, who actually should be the person giving this talk, but she is in the far north of Canada doing field work still, so she was unavailable. Emily came as a student to us 3 years ago, and I gave her this project, and she ran away with it and did a really great job. So we had the 5,500 photos, the oblique aerial photos, and they were already digitized. And then she did some enhancing and standardized the geometry to get the fiducial marks on each of the aerial photographs correctly lined up with each other, and then threw that into the structure from motion software. And what it does is then it goes through sequences of photographs, finding common points, extracting them, and there's a lot to be said about that, but basically you find points as many photos as possible, and then you use that to generate a point cloud. Now, the problem then is these are just they're arbitrary locations. You don't know where they are, but with the aid of the orthophoto that we have now, the reference orthophoto, it's possible to go through and find as many points in the point cloud as you care to find in the time that you have. And I don't remember the exact number that Emily ended up generating, but it was in the tens of thousands. And that allows you then to make a sparse model with absolute positions. And the point clouds can be, like I said, can be sparse in some places, but then you can fill that in and then generate a digital elevation model. And that's what she did. These are generated at 20 and 50 meters, and they cover nearly all of the archipelago. And an orthophoto as well, also from these 36, 38 photos. And with those two things in hand, you can do interesting things like generate can say an aerial photograph anywhere you would like to, and then compare it between the modern day and in 1936. So this is Blomstrandbræen, which is near Ny-Ålesund, and it's retreated about 3.5 kilometers. And these are very useful photos to show people, to give them an idea of the changes that are going on. But really, the centerpiece of all this work is the difference then between the 36 and the 2010-ish DEMs. And the red then is in this color map is minus 150 meters, and the darkest blue would be 150 meters plus. And you see it's very dominated by red. Everywhere nearly is losing mass, and particularly at lower elevations. Where you do see some mass gain, that's either due to reorganization due to glacier surging, which I don't have time to go into, but dynamic changes that are short term. And there may also be some areas of higher elevation where there's been increase in elevation due to increased precipitation. But if you add up the entire area, then you see that it's overwhelmingly negative. And the outlines of the glaciers then allow you to say that it's the whole area shrunk by about 3,000 square kilometers, 7% of its extent in 1936. And the mean ice thickness was reduced by 26 meters. So that's about 35 centimeters a year, or a total 600 gigatons, or about 8 gigatons per year of ice loss going out to sea. And that's about 1.4% of the global mean for that period, 36 to 2010. We then can compare that to a recently published compilation of previous estimates for all of Svalbard in Frontiers by Schuler et al. The rectangles show the temporal extent on the x-axis, and on the y-axis, the error bars, more or less. And then here's our estimate, which has pretty good error bars because they're such a long time period here that we really beat down the errors in each of the individual DMs. We know by looking at 1990 DMs where we have them that we could partition this more or less something like this, where there's more of the melting is occurring later on in the record. And that's consistent with what we're seeing on Svalbard in terms of temperature increases, that the recent decades, we're seeing increasing summer temperatures, annual temperatures, and therefore we're going to see increased losses, and that borne out by all these various estimates. One of the innovations was that Emily brought to bear here was to estimate future changes using space for time substitution. And the idea here is that on a glacier by glacier basis, you can calculate the average elevation change. And you see there's a spatial pattern to that. And it's quite similar to the summer temperature spatial pattern. And in fact, it's a correlation then between summer temperature and the elevation change on a glacier by glacier basis. And so you can then say, well, all right, we know what the situation is in southern Spitsbergen now, and if northeastern Spitsbergen were to have summer temperatures like they are now in southern Spitsbergen, then you could say something about what the elevation change will be in the future. And then we can apply this sort of correlation to future climate change scenarios to estimate the future ice loss. And here we then used 3 different scenarios, 2.6, 4.5, 8.5. And just to remind you that 2.6 is when we manage to get a grip on things, and 8.5 is business as usual. And by making this space for time substitution, then that allows us to estimate what the ice loss will be by 2100. And doing this, then we get estimates ranging from about 67 centimeters per year to 92 centimeters per year, depending on the scenario. And that's about 2 to 4 times the 1936 to 2010 rate. So quite a substantial increase. How does this compare with previous studies? This is a slightly complicated diagram, but on the x-axis is the total sea level equivalent, which will be lost by 2100. This is 0. And then here are our results in the red box there. And you can see that they differ quite substantially from some of the previous estimates. Our most negative result is still quite a bit less than some of the others. And in fact, some of the other estimates have even lost more ice to sea level than is available from our estimate of the total volume of Svalbard. So this estimate, as I said, of say roughly maybe half of the remaining ice volume in the very worst case by 2100 is substantiated in part by observations of what reconstructions of what the geometry of Svalbard might have looked like during the Holocene climate warming, where there were greatly reduced ice masses, although still extant. However, so our most extreme scenario, as I said, was about 90 centimeters a year, and if we manage to curtail our CO2 use, we're still up for 67 centimeters a year. However, the most recent mass balance, which I'm estimating using Arctic DMs, and I have no time to talk about that either, we're already at about 65 centimeters a year for this more recent period, 2013 to 2018. So no cause for celebration here. To conclude then, we can use DMs from historic photographs and combine them with modern DMs and get updated elevation data for using these older photographs, and then calculate long-term mass balance. And then for this historical period, we're getting, well, you can see I already told you those numbers. And space for time substitution is used to project to 2100, and then we're getting 2 to 4 times the 1936 to 2010 mean. And I will conclude there.
Awesome. Thank you, Jack. That was very, very informative. Any questions for Jack on his presentation? Oh. Anyone?
It looks like there's one in the chat, Joe.
Oh, yeah, Jack, do you see that? How reliable are, from Roger, how reliable are the 1936 higher elevation data given the issue of photo saturation?
I don't have that number in my head. I refer you to the to the Nature paper. Yes, the upper elevations will experience that, but it was surprising how much structure was available in them. So it's better than you might have imagined. How's that for a Weasley answer?
Now, by structure, do you mean shadows from higher surface slopes in the, like, going over mild topography, that kind of thing?
It could be anything that you can see from two different or several photographs that would then allow you to correlate a something on the glacier surface or on the surface in general between sequences of images.
Catherine.
I thank you both for your talks. My talk is from educating the public on the concern about sea level rise. And I think the general public thinks that the 7 meters from the melting of all of Greenland's ice sheet is unlikely to happen soon, you know, maybe in their lifetime. So I think that the public can kind of dismiss that. I got out my ruler and I was looking at 3 millimeters, which is what we're seeing per year. And that's like half the thickness of my cell phone. And if I'm the general public, not, you know, super eager to be persuaded, I can say, well, you know, that's nothing. And Christopher, I appreciated your reference to the size of the city of Miami, which is at sea level. I just wonder if either of you might like to say, you know, what is the optimal way to convey to the public what could happen in the next 5 to 10 years? Thanks.
Well, I can make a very quick comment, which is in the longer version of this talk that I have a picture of a bathtub filled to the top. And then you can say, yeah, well, 3 millimeters, that's not very much. But 3 millimeters in your bathtub is water all over the floor, downstairs, and so on. And so it's year after year, another 3 millimeters. Yeah, 1 year, not so much. 10 years, 20 years. And you only have to show a picture from New Orleans to show what happens when you maybe have a few millimeters too much and it breaches the dam and the levee. And so, yeah, very, very clear that the 3 millimeters doesn't seem much, but.
I have a family anecdote that I use pretty frequently when I give public outreach talks, in that my extended family has had a place on the upper eastern shore of Maryland since the late 1940s. And Grandpop's dock goes underwater with surprising regularity now during the king tides, during the storm surges. And as a kid, I remember going out on the end of that dock, and at low tide, you were way above the water surface. And nowadays, the water is up on, on the joists, on the decking boards, up over the bulkhead, and the pictures are very powerful when I've used them, relating to this is what it adds up to being, for people all along the ocean sides. Now, admittedly, Maryland is both sea level rise as well as some subsidence from the old glacial forebulge. So it's kind of a worse there than in some other places. But I think people get it when you basically show and say something along the lines of, that's not how Grandpa built the dock. It's that was not the design. Anyway, so that's one thing that I frequently add to my presentations.
I see that Mindy asked if we have detected more accumulation and seasonal changes, and there is a very weak trend on precipitation, slightly positive, but it's offset by the warming, like to such an extent that it doesn't really contribute much. I think that's what you asked.
Michael, do you have a question?
Yeah, hi Jack. I realized the changes are so big there that you don't need centimeter level accuracy in your elevation measurements, but so you can basically do it all with photogrammetry and structure from motion. But have you used at all or thought about using laser altimetry like ISAT-2 or ISAT-1, and would it be helpful? I realized probably not a lot of orbital coverage of these glaciers there. And the other part is I may have missed it, but I think you probably do all over bare ice, so you don't have to at all deal with calculating ice volume out of Föhn, because they're all probably measurements on bare ice, correct?
To the latter point, no, we do have to assume something about changes in the Föhn structure. It's not as problematic as in East Antarctica, obviously, because it's a vastly smaller area. And then to the ISAT question, Ash Morris and Guillermo Holt and others have a recent paper where they looked at ISAT-2 changes. And there are challenges in that, of course, even with ISAT-2, that you have still fairly wide spacing with the tracks. But yeah, you can use that to extend to your reference surface. So once we have this very good 2010-ish reference DM, then we can do all sorts of things in the future, make assumptions about how spatial correlation of glacier change is going. And that's the future. But the challenge is to get the older elevations. And so the real innovation here is that we can improve on the earlier maps by exploiting this sort of software approach. And with the modern orthophoto in hand, we can get not an infinite number of GCPs, but we can really improve greatly the product.
Any other questions? If not, I have a few. So Jack, is Svalbard uniquely well positioned to take advantage from this structure from motion approach, given the data that you have all around the coastline where you can completely encircle it?
No, actually, it doesn't really depend on that at all. What Emily had to do was break it up into small areas, and in some cases, if you would work down one area on one side, say of this strip of land, Prince Claus Forland, because you can't really see anything on the other side, so it works fine in a linear sense. So I believe that someone's doing this in Northeast Greenland with some historical photographs, that some of which are in our library, because Norway was interested in Northeast Greenland at one point.
So I've gathered.
Yeah.
So the best analogy I can think of for the study for Greenland, say, would be Christian Kjeldson's 2015 Nature paper, where they looked at aerial photography. I don't recall if they did structure for motion, but I don't think they did the space for time substitution. They had some other model assumption. So do you think there's potential elsewhere in the Arctic for the application of the same sort of method? Because it seems to give pretty powerful constraints on what the recent state of affairs is and what the future may be.
Yeah, I would say so. I would think so. Some areas will be very, very well suited to that potentially. All you need is some sort of spatial pattern which would allow you to calculate the mass bound sensitivity to a summer temperature change.
Yeah. Cool. Well, any other closing questions or thoughts from anyone here? All right. Well, if not, then thank you everyone for attending. Really appreciate it. Great presentations. Great to see the variety of things that are going on and how we're thinking about past, change, and futures in the Arctic. And thank you, Christopher and Jack, and for your presentations. Very, very well aimed at the audience. And thank you everyone for attending. And we'll see you again next time. And thank you, Liz and Meredith, as well, for keeping us organized.
Thanks for the invite, Joe and Caitlin.
Yeah, thanks. We'll see you again soon.
Good to see you all. Bye-bye.
Ciao all. Bye.